All right, we're going to go ahead and get started. Again, welcome to today's webinar. My name is Matt Christensen. I'm part of the team at Didax, and I'm going to be moderating our discussion today. And David Bernasconi will be joining us as well to talk about making fraction operations a hands-on experience. So we're excited to have David with us as well. Just a reminder, make sure your speakers are on and unmuted. And then just a couple of housekeeping kind of things I want to go over here real quick. First of all, you may have noticed when you signed in that your name was not correct, and we apologize for that. There was an error with that link, but that's easy to fix. What I would ask you to do, just so we know who's here, is if you go down to the bottom of your screen in Zoom, there's this button that says chat. If you would just open that up and type your name in so that I know who's here. One of the things we are going to do at the end of the webinar today is give away a copy of Fractions with Prime Factor Tiles to somebody who's on the webinar. So I want to be sure I have your name so that we can give that away. So I'd like you to be sure that you do that. And then as far as asking questions during the webinar, I just want to review how that's going to work with everybody. At the bottom of the screen, you'll see a button here that says Q&A. You can click on that at any time. It will pop open a new window, and you can just type your question right in that window and send it to us. We'll address as many of those as we can during the webinar today and at the end. But if we don't get to them all, we will send out a copy of the questions with responses to you afterwards. So again, for those of you who've just joined us, I want to make sure that we capture everybody's name who's on this webinar, because there was a problem with that link, and again, we apologize. But down here at the bottom of the screen, if you'll click on that chat button, you can click on that, type your name in so that we know who's here. And again, we will be giving away a copy of Fractions with Prime Factor Tiles at the end of the webinar today. So I'd like to introduce to you David Bernasconi. David is a middle school teacher in Florida. One of the great things about David, and I really like working with David because he's very passionate about students doing a lot of hands-on learning in the classroom. And he really enjoys developing things that his students can use and that he can use in the classroom to make those lessons and activities come alive. And one of those things that he developed is the Prime Factor Tiles system. He started that in his own classroom, and today he's going to share that with you and talk about that a little bit. The product that we're actually looking at is called Fractions with Prime Factor Tiles. So you'll see David using some of these tiles today. What comes in this set for you is 6 sets of the Prime Factor Tiles. They're really ideal for working with small groups of students and developing these ideas around fractions. You'll also get 3 factor finders, which is a nice tool for your students that haven't mastered those basic multiplication facts yet. And then it also comes with a teacher's guide and some activities. And we'll talk about that again after David shows us what we can do. And then just some objectives for our presentation today. We want you to leave today really with an understanding of prime factor tiles. We want you to know how you can use prime factor tiles to help students compare fractions, how they can help students add and subtract fractions, how you can use them to simplify and multiply fractions. And then one of the biggest things is being able to transition students from this hands-on model to a paper and pencil representation of those problems. So we want you to be able to move on and help students make that jump from this hands-on piece to doing it on paper and pencil. And David will model all of that for us today. And so just one last time, for those of you that have just joined us, if you at the bottom of your screen would click on the chat button, make sure you type your name in there, because we do want to give away a set of Fractions with Prime Factor Tiles after the webinar today. So I need to know who is here in order to do that. And at this time, I'm going to turn the time over to David and let him show us what he can do.
Thank you for the introduction, Matt. I'm going to go ahead and get started. And thank you, everyone, for joining us today. As Matt said, I'm David Bernasconi. I teach middle school math, and I have developed the Prime Factor Tile system and method. This was developed in particular to help students perform fraction operations by addressing the 2 primary challenges that many of these students face with fraction operations. Identifying the factors. It's always a first problem they have, and then recalling the correct rule or algorithm to follow. So with the prime factor tiles and system, every factor can be seen and manipulated. So with the color coding feature, all the common factors are going to stand out, and by physically moving the tiles around, your students are going to learn the steps in these problem-solving processes. One thing I really want to make clear at the outset is probably the biggest hurdle with students performing operations with fractions is a lack of conceptual understanding. So today I'm just focused on the procedural side of things and using the tiles to perform operations and calculate answers, but it's so important that you root your procedural teaching in a conceptual understanding. I got 2 little videos at Didax, prime factor tiles, landing page at Didax, one with coins, one with pizza slices that show you how this can be done. Let's get started right away. Again, prime factor tiles. Prime factors means you can only represent composite numbers as a product of primes. So if I want to start out by representing 25 as a product of prime factors, well, that's pretty straightforward. That's just 5 times a second 5. Now, one thing we don't do is use that multiplication symbol when we're just representing numbers. And so the first rule that everyone should recognize with prime factor tiles is when you see 2 tiles side by side horizontally, they're being multiplied together. So this is not 55, this is 5 times 5, or 25. So we'll go from representing 25 to representing the fraction 25/30ths. Matt mentioned the factor finder earlier, and this is just a resource your students can use if they don't have instant recall of times table facts. And they could look up that 30 is 5 times 6. I've got 5 as a factor. Now there's no 6. The reason is 6 is a composite number, and that would be the product of 2 and 3. So now we've got 25/30ths. And if we were to try to simplify 25/30ths, this is where the color coding feature comes in. We're looking for a factor common to the numerator and denominator. That green tile in the numerator and denominator just stands right out, and that lets me know that 5 is a factor common to the numerator and denominator. And there's several ways to look at this. I can see this as 5/6 times 5/5. Or I could see this as 25 dividing out of 5 to leave 5, and 15, or sorry, this was 30 dividing out of 5 to leave 6. Now, no matter how you do this, 5 divided by 5 has a value of 1. Any number divided by 1 is the number itself. Or we could see this as 5 divided by 5 has a value of 1. Any number times 1 is the number itself. And so whenever we have a common factor to the numerator and denominator, it divides out to equal 1. And that's really the starting point of the system here. Pencil and paper, you would teach your students to take any composite number and write it as a times table fact. So you'll notice here I didn't use prime factorization for the 6. I identified 5 as a common factor just from the times table facts, and that reduced to 5/6. Now, sometimes they might have to go a little bit further, break that 6 down into a 2 times a 3, but we can be pretty confident with 5 as a prime factor that there's no common factor to 5 and 6. Next up, let's compare a pair of fractions, 5/9 and 2/3. So I've got 5/9 and 2/3. And when your students are comparing fractions, one thing that we often do is we make equivalent fractions. Equivalent fractions with like numerators, or it's more practical to make equivalent fractions with like denominators so that we can then set up for adding and subtracting fractions. At the younger grades, lowest level, the students will make multiples. And we can already see that 3 times 3 would make 9. So first thing is to always check, can one denominator be multiplied to make the other? And in this case, we could take our 2/3, and if I multiply that denominator by 3, I'd get 9. And we're back to equivalent fractions, where I'm multiplying by 3/3. And I'm changing 2/3 into 6/9. And now I'm comparing a pair of fractions where the denominators are the same. And we want to know, are they equal? Is 5/9 greater or is 5/9 less? And so my original 2/3 is still visible right here, but I'm comparing 6/9 instead. The denominators are the same. My numerator 6 greater than 5. I can remove these now, right? Again, I'm just dividing out that 3/3 that I had multiplied in before, and 5/9 is less than 2/3. Pencil and paper. You want to show your students that they can just take this 2/3 and multiply by some factor over itself to create an equivalent fraction, and then just write it below. Bring the 5/9 down below, and we're making this comparison. And once I know here at the bottom that 5/9 is less than 6/9, I can come right back up here in the top, and I've got my original 2/3. I can put that inequality symbol there. This leads very nicely into adding fractions or subtracting fractions. The step that you take before adding or subtracting is ensuring that you have like denominators. So I've got 5/6. That denominator would be 2 times 3. And then 7/10. 7 in the numerator, and 2 times 5, 10, the denominator. And as we looked at earlier, when it was the 5/6 and the 2/3, is those denominators, and the denominators not matching. And this is something that you want to really work on conceptually. And the fraction circles are great for that, and making the equivalent fractions or the fraction strips in reference to the number line. With lower numbers, doing multiples of 6, 12, 18, and multiples of 10, 20, 30, until you get a common multiple, that's a great place to start. The problem is when you get to larger numbers in middle school or in high school, or you get to variable factors, rational expressions in algebra, that technique doesn't work anymore. And it's important that the students have another strategy where they look inside those numbers at the factors. Now, every multiple of 6 will have 2 and 3 as factors. So I know when I'm trying to find a common multiple with 10, unless I have 3 in that multiple of 10, I won't have all the factors of 6. Now, the same thing goes with 10 having 2 times 5. Any multiple of 6 already has 2 as a factor, but unless I have 5 as a factor in that multiple of 6, it won't match a multiple of 10. So we identify the factors that are common to the two denominators, a 2 common to both, and then the factors that are not common, the 3 and the 5. So I would need the 5th multiple of 6, and so we're creating an equivalent fraction. I'm taking my 5/6 times 5/5 to get 30ths, 5 times 6. And I'll take my 7/10 times 3/3 to get 21 30ths. And you can always confirm that the denominators are alike if you find the same factors. 2 is a factor, 3 is a factor, 5 is a factor. So we take our fractions as given, we make equivalent fractions with like denominators, and now we're ready to add those fractions, or if we like, we could subtract those fractions. So it wouldn't matter whether it started out as an addition problem or as a subtraction problem, the method is still the same. Make those like denominators by identifying your common and your non-common factors. So if we add this together, we get 25 plus 21, 46 30ths. Pencil and paper. Off to the side, multiply by a factor over itself to get an equivalent fraction. And so my 5/6 times 5/5, I'll get 25 30ths. The 7/10, we multiply off to the side by a factor over itself, 3/3, to get 21 30ths. Starting point, of course, was recognizing what is the non-common factor in each of those denominators. 6 had a 3, but lacked the 5 that was in 10. 10 has 5 as a factor, but it lacks the 3 that's in 6. And this is a great little strategy to get common denominators that are the least common denominator of the two numbers. You'll notice here the answer, 46 30ths. Well, I can't represent that with prime factor tiles. And this just emphasizes that the purpose of the tiles isn't for displaying answers. The purpose is for calculating those answers, for going through the problem-solving steps, being able to see the factors, being able to manipulate those factors with your hands, and then being able to transition to pencil and paper. So most of these problems that I make up, are going to come right off the multiplication table. All of those numbers on the multiplication table are factors of 2, 3, 5, and 7. All right, let's go ahead and try something else a little bit with fractions that you see in the elementary grades, and that is fractions greater than 1, also called improper fractions, and mixed numbers, also called mixed fractions. And so if I start with 7/3 as a fraction greater than 1, 7 in the numerator, 3 in the denominator. Now with prime factor tiles, I can rewrite 7/3 as a mixed number. And I'm looking at the numerator being greater than the denominator. And I just want to break that down into some number of thirds plus another number of thirds. I want to set this up as an addition problem. Some number of thirds plus more thirds. So my 7/3, how many groups of 3 things in 7 objects? And it's so important that we reinforce conceptually what does it mean to divide, right? A fraction being a numerator being divided by some denominator. Well, that's 7/3. I could split that into 6/3 plus 1 more third. Now, why 6/3? Well, I need a multiple of 3 to make whole groups. 1 group of 3 is a whole, 2 groups of 3 is 2 wholes, and so forth. So I've got 2 times 3/3. That's my 6/3, and 1 more third for a total of 7/3. Well, 3 divided by 3, the color coding feature of the prime factor tiles. 3 divided by 3 is just 1, and 1 times 2 is just 2. My 7/3 is equal to 2 and 1/3. I can leave 2 up here, or I guess I could put the 2 right there. Again, the focus isn't on displaying an answer. The focus is on performing the operation or the calculation. How do we do this with pencil and paper? I want to see my 7/3 as a sum of 6/3 plus 1 more third. Why 6? Because it's a multiple of 3. Here's my remainder, 1/3. 6/3 simplifies to 2 and the 1/3. We could do the reverse, starting out with a mixed number or mixed fraction, and then trying to turn that into an improper fraction, or a fraction greater than 1. So if I start with 3 and 2/5, well, I've got the whole number 3 plus 2/5. Now, I can take that whole number 3 and make it into any fractional part I like. I could multiply by 3, my 3 by 2/2 and get halves. I could multiply by my 3 by 3/3 to get ninths. Well, I'm looking to get fifths. So I take my 3 and multiply by 5/5 and convert the whole number part into 3 times 5, 15. So 15/5 plus 2 more fifths, and I'll end up with 17/5. So once again, with pencil and paper off to the side here, my whole number 3 times 5/5 to match the denominator of the fractional part. And I've got 15/5 plus the other 2/5 for a total of 17/5. So one thing I'd like you to notice as we move through these brief and quick little demonstrations of what you can do with prime factor tiles for fraction operations is how everything is related, and we're always looking for common factors to the numerator and denominator, how we're always looking for equivalent fractions. Well, when we multiply fractions, we're going to take what we know about simplifying and actually simplify first. 5/8 times 2/5, 5, and then 8, 2, times the second 2 is 4, times 2 is 8. And I'm going to take my 5/8 and multiply by 2/5. Now, one thing that's really important when we move to operations such as multiplying with fractions is trying to make sense out of it. So very often it's just numbers to the students, and they'll come up with a crazy answer without recognizing that it makes no sense. So I'm just going to show very briefly how I can take that 5/8 times 2/5 and try to make some sense out of it. So I've got a little fraction circle here. So this is 8. So I've got 8/8. I've got a whole, broken into 8 equal parts. And if my fraction starts with 5/8, that means I had a whole and 1, 2, 3 were taken away. And that might be something as simple as buying a pizza, 8 slices, and having eaten 3 slices, having eaten 3/8 of the pizza. Well, what remains? 5/8. Now, a real world problem here. Leftover pizza, some fraction, 2/5 of what remains being eaten later, maybe for a snack, maybe for lunch the next day. So I'm looking for 2/5 of the 5/8 that remain. Well, shows this on purpose, obviously. I've got 1, 2, 3, 4, 5 pieces, right? I divide my 5/8 into 5 equal parts, and I want 2 of those 5 parts. So my solution should be right here, 2/8. Well, with prime factor tiles, I show multiplication of fractions by just sliding the numerators, the factors in the numerators together, sliding the factors in the denominators together. And now we're just identifying factors common to the numerator and denominator. Right away, that pair of 5s stands out, and a pair of 2s stands out. 5 common to the numerator and denominator, a 2 common to the numerator and denominator. Now, you'll notice I don't have a factor here. I got to bring in this 1, and I've got 1 times 10, and I've got 4 times 10. So this was 10/40ths if I had chosen to multiply first instead of simplifying first. Very often, though, we're going to simplify to lowest terms, and I'm really looking at 1/4 times 10/10. Well, 10 divided by 10 is just 1, and any number times 1 is the number itself. It's just clear right out of our problem, and we're left with 1/4. Now, as far as reinforcing that answer, 1/4, well, here's my 2/8 that go together to make a 4th. I've got another pair of 8s that make a 4th. And if I bring in the 3/8 from the original whole, sure enough, I've got 4 equal parts, and one of those 4ths is what's represented here. Now, the transition from multiplying, well, actually, let's just show pencil and paper. So pencil and paper, what we might show here is that first fraction, 5/8, written as a product, times table fact for 8, 2 times 4, times the 2/5. And we're just identifying factors common to the numerator and denominator. So in this case, they happen to be prime factors. Sometimes they're going to be composite factors. Sometimes we break the primes down, or the composite number down, into a prime times a composite or a composite times a composite, and you just go as far as necessary to reach simplest form or lowest terms. All right, last up, just a quick little example with division. And I think it's really important that we start talking about division by really reinforcing that division is just the inverse of multiplication. For me, dividing fractions by fractions just is so confusing, and I try to think of a context that really makes sense or would make sense to my students, and most of the time I'm at a loss. What I really like to think of it as is, if I've got 8 divided by 2, as you see on the card here, and I bring out these circles again, little pieces of the fraction circles, 8 pieces, 8 things being divided into 2 groups. Well, here's my 2 groups. And everybody knows that 8 divided by 2 is 4. 1, 2, 3, 4. 1, 2, 3, 4. Well, instead of dividing 8 by 2, if I multiplied 8 times 1/2, I'd still get 4. Half of the 8 tiles over here to the left, the other half of the 8 tiles over here to the right. So we reinforce division as the inverse of multiplication with whole numbers before we do anything such as divide with fractions. I apologize for that announcement in the background. I'm obviously still at school. So if we want to divide 5/12 by 3/4, this one I'd have a little bit more difficult time modeling physically. Now, as far as the procedure of dividing with fractions, I'm going to take my 5/12, 2 times 2 is 4, 4 times 3 to make 12, and we're going to divide that by 3/4. 3 in the numerator, and 2 times 2 is 4. Now, we all have our pet peeves. One of mine is cross multiply. Because in middle school or with high school courses, usually when a student says cross multiply, it's the wrong operation or the wrong application. Very often this is taught in the younger grades for comparing fractions. Really not a good thing to do. Instead, we want to see this as, instead of dividing by a number, we can multiply by its reciprocal. In addition to cross multiplication, keep, change, flip, or keep, change, opposite, or keep, change, change. These are very common strategies taught to students, but they're not necessarily anchored in a specific problem. So if I'm dividing by a fraction, there's nothing about keeping, changing, or flipping that correlates with dividing and fraction. But here's what does correlate. Instead of dividing by a number, we can multiply by its reciprocal. And so all I'm doing is I'm recalling that inverse operation between multiplication and division. What we just reinforced with whole number values. What we just reinforced, 8 divided by 2 is 4, 8 times 1/2 is 4. Dividing by a number, same as multiplying by its reciprocal. And here we are again, right back to factors in the numerator, factors in the denominator, and identifying factors that are common to the two. And so I've got a 2 common to the numerator and denominator. 2 divided by 2 is 1. I'm going to pull that right out. I've got a second 2 common to the numerator and denominator. 2 divided by 2 is 1. That's going to drop out as well, and we're left with 5/9. Pencil and paper. We take our 5/12 and we speak out loud. Instead of dividing by a fraction, we can multiply, as you cross out that division symbol in the 3/4, by its reciprocal, as we write 4/3. And now we've turned a division problem into a related multiplication problem. Common factor to the numerator and denominator is 4. 4 divided by 4 is 1, and we're left with 5/9. We're about out of time. This is all I've got for you today. This is just a brief introduction to the use of prime factor tiles with fraction operations, primarily for the elementary grades or remediation right through middle and high school. Thank you again for tuning in, and I'll turn things back over to Matt.
Great. Thank you, David. We appreciate your time to do this, and we appreciate the time of everyone who's been able to join us today as well for this presentation. I just have a couple more things here, and I'm going to share my screen with you. All right. So just a couple housekeeping-ish kind of things. We know a few of you came in late, and we did have some problems with names showing up correctly as you came into the webinar. So once again, for those of you that haven't done it, if you can click on the little chat icon down here at the bottom, click on that. Just type your name in there so that we know you were here, because we are, in just a minute here, going to give away a set of fractions with prime factor tiles to one of you who's on the webinar with us today. And then also, if there were any questions, there is a Q&A here section that you can type that in. Any questions that you might have that we can answer for David real quick, or as I said, we can hang on to those and send them out to you later as well. And then just to review here, so fractions with prime factor tiles, which is what David was using today in his session, that set does come with 6 sets of prime factor tiles. It's really, as I said before, designed for small group instruction with students as they're learning these skills and concepts. It comes with 3 factor finders, which I'll show you in just a minute, as well as a teacher's guide and activities. You can also find additional resources on our website. You can go to didax.com/PFT. What you'll find there are over a dozen videos of David demonstrating these concepts in different pieces, different chunks, and he does a really good job of building that conceptual foundation that he talked about at the beginning as well, and then moving through examples like you saw in the webinar today. It also comes with a teacher's guide with activities. You can find that on the website there. You can find activities to do with the prime factor tiles. And then the factor finder is on there as well. Again, this is a tool, a resource for your students that have not yet mastered those multiplication facts. They don't have that quick recall yet. They can use this to identify the prime factorization of numbers that they're working with. And also on there, excuse me, there's also a set of correlations to various standards. So now the moment you've all been waiting for. The winner of the free set of fractions with prime factor tiles, and again, we thank you all for being on the webinar today. The winner of that free set of fractions with prime factor tiles is Elizabeth Connellan. So Elizabeth, congratulations. I'll be contacting you by email to get an address where we can send that to you. We'd also ask all of you to check your inbox after the webinar. You will get an email following up on the webinar that will have a 20% off discount on fractions with prime factor tiles and other Didax items. We'll also have a link to the webinar because we want you to be able to view this later, share it with friends, others who weren't able to join us today. And again, thank you for joining us. I don't have any questions here in my Q&A box. If you did have any questions, you can contact us directly and we'll be happy to answer those. You can find more information about prime factor tiles and all the other Didax items on our website, didax.com. You can also contact Ann McManus or myself, Matt Christensen, directly. Our email addresses are there and we're happy to help you as well. So again, thank you for your time. We really appreciate you taking half an hour out of your day to share that with us. And we will definitely look forward to hearing from you and hearing about your experiences with materials. Thank you so much.